Ladies and gentlemen, welcome to our next chapter in this. We're going to talk about Newton's laws. So it's going to be three laws that we're going to be talking about. And so let's get on with the first one, and that is, let me get my pen. Give me a pen. Oh, it's over here. It is Newton's first law, and basically his law says that you have an object at rest, it's going to stay in rest. It's not going to move until you put another force acting on it. And if it's in motion, it will stay in motion unless there's another force acting on it. So if there's nothing else acting on this ball and it's staying there, and you push it, you add a force to it, it's going to start moving. Newton's first law. That object is going to stay at rest until something moves it, or you have some type of force acting on it. For something in the 1600s now, it's a very theoretical idea. Now, in this, he talked about something called inertia, which is defined as the resistance of an object to be moved or responding to a force acting on it, and mass as a direct relationship with inertia. Mass is proportional to I. The bigger the mass, the more inertia. And this is what this last part says. And so this means that if you have two objects, one is about 1,000 times more than the other, that small object's not going to do anything to the big object. Well, the big object is going to have more influence on that small object. And that's all our inertia means. And we can see it when you try and push a wall down. The wall has a lot more mass than you, and you don't have enough force to knock it down. Therefore, it has inertia. Even though you're applying pressure, you're applying a force, it's not going to do anything. Now, the second law is basically this equation. Force is equal to mass times acceleration. So force is equal to the mass in kilograms times acceleration and that's meters per second squared. Now, ma, mass times acceleration, the units of force is newtons, which is the same thing as going kilogram meter over second squared. So these two are basically the same, and you can see it written either n, capital N, or kgm over s squared. Both of them are valid units. And this is Newton's second law. Simple, simplistic, done. Newton's third law, what everybody likes to correct. If two objects interact, force on one on object 2 is equal to magnitude to the force on 2 on object 1, but in opposite directions. Okay, let's rephrase this. If object 1 hits object 2, the amount of force that's acting on object 2 is equal to the amount of force acting on object 1. But in the opposite direction. So if object 1's force is this way, object 2 force is going the other way, but directly opposite directions. Newton's third law. If you have two objects, again, the two objects must interact. The force on one is equal to the force object 1 acting on object 2. You're going to have opposite force acting on object 1 from object 2. The magnitude is going to be equal, but the force is going to be opposite. Now, the next is net force. And you've been dealing with some of the problems. Sums all the forces acting on an object or a body. If the net force is 0, the object is at constant velocity, even if that velocity is 0. So if you got an object moving in space with no other forces acting on it, and you apply a force on either side of that spaceship, the net force is still 0. It's not going to change its velocity or the direction of its velocity. But if the net force is unequal. If net force is not zero but it's positive, you're going to end up getting a change in velocity, change in direction. And this is what we mean by net force, and this is what what we're doing with some of the problems. So let's look at hammering a nail. So we've got a nail. And here it is sitting on a piece of wood. The wood has 1 Newton going up. The nail has 1 Newton going down. And it's got a little point at the end of these nails. And so what happens, you got a hammer. It's going to hit downwards at 10 Newtons. This is going to reply at 10 Newtons. But what happens is that the force at this point is going to be 11 Newtons, which is greater than 1, and it's going to force the nail down. So when we're hammering a nail, we're actually overpowering the force pushing up against the nail. And that's the nail goes in. And this is where we mean by unequal forces. You actually have a net force acting on this point right here. Now we have field forces. Field forces are paired well. So we're talking about gravity, electricity. Gravity, if you have the Earth, and you got a watermelon. Watermelon is 1 kilogram. The Earth is 1 times 10 to the 9th kilograms. You drop the watermelon off the roof, it's going to feel the pull of the Earth down. The watermelon is trying to pull the Earth as well, but since the Earth is so massive, has a large inertia, it's not going to move. And what we see is the watermelon crashing to the Earth and going splat. And that's what I mean by field forces, and that they are paired. Couple of terms to talk about. One, if the forces cancel each other out, they're classified to be in equilibrium with each other. And we have a simple problem that describes this. If we've got a car moving down the road, it weighs 450,000 newtons. So here's the road, here's my car. Its force, its weight is 450,000 newtons going down. The road is actually applying the same force going up. So if it's in equilibrium, it's not going up and down. The engine is providing 6,500 newtons going this way. Down the road, air resistance is 6,500 newtons going the other way. So if it's moving, the velocity is not changing. We've got constant acceleration, zero acceleration, constant velocity, and all the forces acting on the car are canceling each other out. This is what we mean by equilibrium. Now we have something called non-equilibrium. Ooh, this is going to be interesting. So we have a physics book on a ramp, 35-degree angle. Friction is 11 newtons. Force on the table on the book is 18, while the force of gravity is 22. Let's draw the free body diagram and take a look at this. So we've got a ramp. So what we're going to do here, we're going to draw a ramp. I'm going to draw it down this way. And the book is on top of the ramp, so we're going to draw a book. Now we're going to go back and say we got a 35-degree angle, friction is 11 newtons. So here's my 35-degree angle. Going back is 11 newtons. Force of the table on the book is 18 newtons. So going this way is 18 newtons, and going down it's going to be 22 newtons. So if I draw a free body diagram, I have gravity going down At an angle, I have 18 newtons. That's what we call the normal force. Normal force, which is the force perpendicular to the surface. And we have 11 newtons of friction going the other way. And what's the question asking us? Oh, the net force on the book. So let's figure out the net force. So far, this is y. I got two things at an angle. We're going to rename the x and y axis. So realize we got this. I'm going to take this and rotate it this way so that we have this, where this is 11 newtons and this is going to be 18 newtons. Let me double check. Yep. And this is 22. Now, where's my angle? Which one of these is going to be 35? Now remember, if we come down here and go this way, this is 35. So if I rotate it, this is my right angle. So this is going to be 35, because this one right here is this right here, which is not 35, but 55. So here's my 35 angle right here. We're changing perspective. We're moving x and y over. Now we just have one angle we have to worry about, not two. And so we need, if I redraw this, I want to know y, I want to know x, and this is going to be 35 degrees. So, and this is 22. So 22 times sine of 35 is going to give me my x, while 22 times cosine of 35 is going to give me my y. And so if I get my handy dandy calculator out, go 22 times sine of 35, x is going to be 12.6. Y is going to be 18. So draw this again. Now I got components in both x and y. This is 18 going up, 18 going down, 11 going to the left, and 12.6 going to the right. My net force, this cancels, 12.6 minus 11 is going to be 1.6. My net force coming down here is equal to 1.6 down the slope. So we go back to this previous question. We're going to have a net force of 1.6 going down the slope. And that's how you solve those type of problems. And that's the end. Thank you.